Okay, we are looking, get a light on there so we can actually see what we're looking at. Lesson 2-3. We are picking up where we left off yesterday. We had talked about example 1 yesterday. And example 1 was graphing the transformations of the monomial functions. So we took an x to the third, and we looked at how we could transform that. We also talked about x to the fourth and how we could transform that. Okay, for those of you that missed, the recording is on Schoology from yesterday for anyone that needs to go back and get that. Or you're always welcome to take a picture of my notes if that would help to be able to look at them later. We're looking, moving on, to example 2 today. And in example 2, we're graphing combinations of monomial functions. So yesterday was just an x to the third or an x to the fourth. Today it is an x to the third, add another monomial. So in this case, we're either adding or subtracting x. We're asked to do a couple of things here. We're going to graph it. We're going to locate its extrema and zeros and explain how it's related to the monomials from which it is built. Okay, a little bit of vocabulary here. We're going to graph it, but it also asks about the extrema. Do you remember what we mean when we use the word extrema? Okay, yeah, max and min. So you start off saying hills, so like hills and valleys. But those hills and valleys specifically, the official wording, okay, good mathematical wording is the maximums and minimums. So when we talk extrema, we're going to be talking about maxes, max and mins. Okay, so extrema. I know some of you had forgotten that word, I can guarantee it, so just kind of throwing that out there. And then zeros. What do we mean zeros? X.
Like the points are the graph across the x-axis?
Yeah, it's the x's, it's the points where it crosses the x-axis, so x-intercepts. Okay? So when we talk zeros, we're talking x-intercepts. Again, just reviewing vocabulary because we all tend to forget vocabulary at times, myself included. So, okay, looking at example A. Example A is f of x equals x cubed plus x. Now, before we go to the calculator, and we will look at the calculator here, but it's the highest power is x to the third, yes? Can you visualize what an x to the third graph looks like? Okay. The little thingy, as he's drawing it in the air up here, okay? So it's that increasing graph we looked at yesterday on part A on example 1, didn't we? Okay, so it's that increasing graph. Now, let's, right here, I'm going to draw a small xy axis. So that cubic graph is going to have that general shape, that general increasing shape. Now, it's going to be slightly different because we have the plus x. But I'll be honest, it's not going to be too different in this case. So you can think about like some xy values. If we put in 0 into this equation, I can zoom in so everyone can see better, virtual and present people. And virtually you have to speak up if something is going astray, but hopefully you guys can see decently there. X cubed plus x, if we put in 0, what's 0 cubed plus 0? 0. So we have the ordered pair 0, 0. What happens if we put in 1? Normally when we put in 1 to just x cubed, we get 1 comma 1. But what happens if we put in 1 this time? Yeah, 1 cubed plus 1, so 1 plus 1 is 2. So then this ordered pair is 1 comma 2. Put in negative 1. Negative 1 cubed plus negative 1. No?
-2.
-2? Negative 1 to the third is negative 1. Plus another negative 1 makes it negative 2. Okay, those dots kind of appear to be in a straight line, but you know better. They're not actually in a straight line, right? But they do carry that same shape. Okay, they carry that same basic shape of y equals x cubed. Now, I don't know if you have or not, and I know my calculator is not showing up well on the virtual screen. Whoops. If I graph x cubed plus x, I'm going to do a zoom 6. And it just does not show up well, and I can't get the right combo. Yeah, I don't think you guys can see it. So virtually, you guys all have your own calculators, right? So what I would say is you can see it on your own calculator, the y equals x cubed plus x. Okay, I've just got that on the standard 10 by 10 screen right now. Now, as we look at this, okay, let's talk extrema. What do we have in the way of extrema here? What do we mean extrema here? No, we're not talking infinities here. We talk mids and okay, so when we talk mids and maxes, like, let's see, Ethan used the word hills, and I think I threw in valleys earlier. So, do we have hills and valleys here? I mean, the idea is, do we have a spot where this graph comes up and hits a high point and then goes back down? No, not really. Do we have a point where the graph is going down, it hits a low point, and then turns and goes back up? No. Do we have any mins and maxes? And that's the key. We don't have any mins and maxes here. Okay? And I'll show you one here in a moment that does have mins and maxes that will help distinguish the difference, okay? But in this particular problem, this graph is purely just an increasing graph. It's just continually going up. So because it never turns and goes back down or anything, there's no mins or maxes. So first thing I'm going to state here is that on this particular graph, there are no extrema. And when I say no extrema, I am essentially saying no mins or maxes. After you get written down that there's no extrema, the next thing you want to think about, they ask us for zeros. So what am I asking when I'm asking about zeros? Yeah, x-intercepts. Where do we cross the x-axis? And we cross the x-axis at 0, 0, which I don't really need the ordered pair. It's at what x value? And the x value is 0. So there is a 0 at x equals 0. Now, excuse me. The final part of this, if you look at the directions, says to explain how it is related to the monomials from which it's built. So what we're looking at is we're trying to look at the relationship between the graph x cubed plus x, which is what I already have the graph of here, yes? And then the monomials from which it's built. So we want to look at what does x cubed look like and what does x look like. Now, for those of you in class, I can graph it just fine for you. For those of you not in class, what you might do is take your calculator. And so in y1, I already have x cubed plus x that I'd already graphed, yes? In y2, I'm putting x cubed, so just the plain old x cubed. And then in y3, I'm putting x. And And I'm going to graph all three of those together so we can see connections there. So I'm going to go ahead and hit graph.
Why are you putting just X?
Because just x is the other monomial here, which is right there. Now, and again, I apologize. This is the tech problem I ran into this morning. You guys can't see anything on my calculator screen, can you?
Why can't
If I-
It's just the way the camera.
It's the way the camera is showing, like, and I haven't figured out a way to fix the problem very well. And I don't, it might be
They don't
because
see what we see.
well,
The calculator.
it's showing a white screen on their on the calculator. And I don't know. See, the thing is, I get a glare back here, but let me try something for a moment. I don't know if I may, see, that's what I have to do. So if I turn the lights on in the classroom, my virtual people can see it better now, can't they? Minus the glare down in the corner. Okay, so I guess I'll just be turning lights on and off is what I'll be doing here. Because I do want you guys, I want them to kind of see here, and it does help some. Okay. Any other time, my virtual people are going to prefer to have the lights off because they have a glare down at the bottom there.
Okay.
Which, as long as they stay out of the glare, it's all good. But now, I am going to zoom in because I want you guys to see that. But right now, as you look at the two graphs, I have x cubed plus x, and I have x cubed. Notice those two graphs are almost identical, aren't they? Now, that line y equals x is just a line going through the middle. When I zoom in, so I'm just going to do a basic zoom in. So I'm going to hit 2. I'm going to hit enter again to get it to zoom in. Notice what happens here. No, he didn't break it. It says invalid dimensions. So I'm going to say zoom 6. Okay, that didn't solve the problem. Why not? Let's window. Oh my gosh. Okay, got it. Your stat plot is still on. Oh, we need to turn that off. I'm sorry, that took me so long to figure out why your calculator wouldn't graph. Okay. Okay. Can everyone see now? To an extent at least, okay? As you look at these, and they're kind of, I've got a zoomed in version here, but my blue is my original. That's the x cubed plus x. It looks a lot like the red, which is y equals x cubed, right? Now, what do you notice about that black line going through the middle? It goes through 0, 0, it's straight, but also do you see right there in the center how it overlaps directly with my blue graph in the center? Okay, that's the effect that y equals x line has on it. So, like overall, my graph looks a lot like the main function, x cubed. But what's happening is the other part, the plus x here, that's determining what's happening around the origin. And so that's making this graph kind of straighten up a little bit so it runs along y equals x. Okay, and that will become even more evident here when we look at y equals negative x about what happens on the next one. Okay, so as we talk about how is this related to the monomials from which it's built, well, overall the graph looks like y equals x cubed. Around the origin, it though more closely resembles y equals x. And that's the gist of what I'm going to write here in the notes, is that I'm going to write the shape is much like y equals x cubed. So shape is much like y equals x to the third. And then I'm also going to say near the origin, so near the center there, near the origin, the shape resembles y equals x.
doesn't y equals x to the third also go through the origin?
It does. Yeah, they both go through the origin, but it's the idea that if you specifically look here, right, specifically there, my blue graph and my black line exactly overlap. Like they have the same angle to them right there at the origin. Whereas my red graph, which is just y equals x cubed, it crosses it, but it doesn't have the same angle. Maybe that's the wording I should be using, is talking about the same angle at the origin. Does that help a little bit? And again, it'll make even a little bit more sense when we go to part B and we look at how that relates.
I mean, it makes sense.
Yeah. Okay, are we good on A? I think I have everything out of the glare so you guys could see to copy down to A, couldn't I? Okay. Let's look at B. B says f of x equals x cubed minus x. First thing we're going to do is we're going to draw a basic graph here. And again, we're going to look at the calculator in a moment, but we're going to talk about it a little first. F of x equals x cubed minus x. Okay, think about it. What happens when we put in 0? 0 to the third minus 0. 0 minus 0, which is 0. So again, we have a point at 0, 0. Okay, good. What happens when we put in 1? 1 to the third minus 1. What? 0. So we have the ordered pair 1, 0. Interesting. What happens when I put in negative 1? 0. Because negative 1 to the third is negative 1 minus negative 1. Turns around, makes it negative 1 plus 1, which is 0. So we have the ordered pair negative 1, 0. Do we really have just a straight line there in the middle? And no, we're not going to. If you've looked on the calculator, you see a little bit about what's going on. But based on the fact this is a x cubed graph, and it's still a positive x cubed, we're still going to have the same basic behavior. And then my graph is going to start low, and it's going to end high. And what you'll find out is that this graph is going to go up through the first point. It's going to turn, go back down, and then come up. And so if I graph this to show you, I'm going to go back to Zoom 6 here. And we have a different type of glare on the calculator, of course. Maybe that's better? Okay, so if you graph, what I have graphed in my calculator right now is just y equals x cubed minus x. If you graph that, what's different? Kind of zigzags back at the origin. If I zoom in, I go zoom to number 2, and I hit enter once I get in there, that shows you a little bit closer up view of what's going in. So notice, it's going up, but it has that brief decreasing moment, and then it goes back up, doesn't it? So the idea goes up, cuts through there, cuts back down, and cuts back up, looking something like this. Now, what's going to make that change? It's that minus x. And we'll investigate that a little closer in a moment. But let's start by talking about extrema. What do you remember about extrema? Do we have any? Last time we decided we didn't have any. This time what's happening? Yeah. Right here, in between -1 and 0, you're going to have a max. Over here, between 0 and 1, you're going to have a min. Sound familiar? Okay, well the directions asked us to locate the extrema. How do we locate the extrema? Yep, on the calculator. So this is where I would encourage everyone to get the calculator and practice, because I know some of my morning class had forgotten how to do mins and maxes on their calculators. Actually, I was going to give the whole ordered pair. Okay, so, well, I was rounding my ordered pairs to 2 decimal places, is what I have written down when we get to that point. Okay, so I have my graph. I like my zoomed in version. I can see a little bit better. Mins and maxes, you go to the calc menu. So second, calc, which is the trace button. And then you can go to either number 3, minimum, or number 4, maximum. I'm going to start with my maximum. Please practice if you don't, How do I left bound? So I want the left bound of my maximum. So I'm going to go over here closer to -1. I'm going to hit enter. For my right bound, I'm going to go closer to 0. I'm going to hit enter. And then for my guess, I'm going to go in between to the top of the hill because I'm trying to find my max. And I'm going to hit enter. Okay, hopefully those are sounding familiar. Yes?
The calculator is doing something wrong.
Okay, I'm going to go with Abby. Let's try Abby's issue first. Or stat plots first off. Oh, no. Okay, so I would on yours go to zoom right there and go down to number screen because there you go.
Oh, what happened?
And that's what I have there.
Yeah. What
Okay.
happened?
You were just really zoomed out. I think it's because it looks like the last time you used it is when we did that stat plot and we had to set the window settings.
Oh, okay.
Yep.
Thank you.
Yep, you're welcome. Okay, did you guys get the same max I did? I realize probably because of the glare my virtual probably can't see it, but -0.5773511 and y value is 0.384900018. Something very similar to that. If I go 2 decimal places, that puts there being a max at the ordered pair, -0.58, comma 0.38. Have you found your minimum? We're closer to 0. My right bound is to the right of the valley, so closer to +1. And then my guess is at that low point. What do you notice about your minimum values? Opposite signs? Same numbers, opposite signs. So it's 0.58 and -0.38. Those are your max and min values. Okay? Second thing we're asked for is zeros. You can get fancy and use the calculator, or you can realize we've essentially already found them. What are our zeros here? The x-intercepts, which are what? Yep. -1, 0, and 1. And you would want to list all 3 of those because you want to list all your zeros when they ask for them. Okay, the last thing is to talk about the shape. And this is where earlier it was describe how this is related to the monomials from which it is built. So in this case, we have x cubed minus x, which means it's built from what two monomials? X cubed and not x this time, but negative x or minus x. So the best way I can show this is if I go in here, we've already got x cubed minus x. And I don't know if this is going to make it worse or better for the moment. But if I have x cubed minus x, I'm going to make my second one, my y2 is x cubed, and my y1 is x. So what I'm doing is I'm graphing them together, and I'm also graphing them as x cubed minus x, and excuse me, it's not supposed to be x, it's supposed to be what? Negative x. I about made a mistake. Now, if you graph, watch what happens. X cubed minus x is already there. X cubed, very similar, right? Y equals negative x is the line going the other way. But, what do you notice about that line going the other way? Well, it crosses the two other graphs, but notice my original graph, my blue graph. Do they run along together for a little bit? Yeah, that y equals negative x, briefly there right near the origin, runs right along x cubed minus x. Okay, and so that's, another example of how that minus x affects our graph, because it takes that shape at the origin. Am I making sense there?
Yeah.
I'm hoping that kind of, okay. But I'm hoping it kind of, the last one, I don't know, it was the same positive, so I didn't feel like it was as easy to see. Okay, so write your explanation down. And again, I'm going to start by saying the shape is much like y equals x cubed. And this time, but we're going to say, but near the origin resembles y equals negative x. So shape is much like y equals x cubed, but near the origin resembles y equals negative x. I'm out of the glare there for you guys to see that, aren't I? Okay. If we can finish the front page and what I want to talk about there, we can at least match up with my morning class. I'd hoped to get one more example in this morning. It just didn't happen, so. Okay, you got what you need there? I'm going to zoom out. And I'm going to go more about talking about the cubic and quartic graphs. I think so. Am I going to kill you guys if I turn off the lights again? Is that a bad thing? Because it really does help with the glare on virtual.
Feels like midnight.
You've got all this sunlight coming in behind you. It's not midnight.
It's
Okay. Oops, it helps though. I need to turn that light back on. Okay. Cubic. We're talking about cubic and quartic graphs here. What do I mean when I say cubic? X cubed, right? So this is the graph we talked about yesterday. We've already talked about today. Y equals x cubed. The basic y equals x cubed graph is like that first one. It's just that increasing graph. Now, we saw an example like this today, right? Where it could also dip down in the middle and go back up. Those are both examples of positive x cubed graphs. Now, what do I mean when I say quartic? Excuse me. Quartic is x to what power? The fourth. Yep, you got it. So y equals x to the fourth. We talked about one of these yesterday for those of you that were around yesterday, yes? Yeah, we up on part 1b, we graphed a quartic that looked like this. It's like a parabola, but is a little flatter along the bottom. These also are all examples of what a quartic graph could look like if it's a positive x to the fourth. It all depends, like this would be just x to the fourth. These would have other x terms in them. So they might have an x cubed, an x squared, and an x in your equation. So it could look like a w, lopsided w, or I don't know what you want to call those, a w where it's not very, not much of a middle there. But those are all examples of what a quartic graph could look like. Okay? Now, a couple of key points to make. You already know this, but as a reminder, if the leading coefficient is negative, the graph will be flipped vertically. So, just like if you have x squared as a right side up parabola, negative x squared makes it an upside down. So what happens with the x cubed graph? If it's negative x cubed, it's going to be upside down. If with an x to the fourth graph, upside down. By w would become an m, so to speak. Okay, so just a reminder that if that leading coefficient is negative, the graph will be flipped vertically. You could say reflected across the x-axis if you want. And then, or one other key point that I'm going to explain here. A polynomial function of degree n will have at most n minus 1 extrema and at most n zeros. Let me translate that one for you. Okay, so important information. A polynomial function of degree n. So whatever your degree is, which degree is your highest power, it will have at most n minus 1 extrema, so 1 less than the degree extrema, and at most n zeros. Okay, so however many degree, whatever degree it was, can be whatever number of zeros it is. Now, because I think it's a little confusing to just understand the example. And I'm going to use the example of a degree 4. What is a degree 4? That's a quartic, right? All of these up here are degree 4 because they're all examples of quartic. So the idea here is if it says degree n and the degree is 4, that means n is 4, correct? Well, what's it mean when it says at most n minus 1 extrema? What do we mean n minus 1? 3, because it would be 4 minus 1, and so that would be saying 3 extrema. Now, technically, it's not exactly 3 extrema, but it is what? At most 3 extrema. And if the degree is 4, what does it mean about zeros? At most n zeros, which would say at most 4 zeros. I'm going to use one of our quartic graphs above to help demonstrate, because I think that's the easiest way for you guys to see. If we were to pretend, I'm going to take the one that looks most like a W, and if we were to pretend that that is the x-axis that I just drew through the core of that W. Okay, so it's quartic, so that means it's degree 4, correct? Now, it said at most 3 extrema. What's that mean? At most 3, what are extrema? Mins and maxes. Do we have 3 mins and maxes here? Yeah, this is an example of the most you could have because we have what? A min, a max, and a min. So there's an example where there are 3 extremas. Now, if I had drawn my x-axis through the first quartic, would that have 3 mins and maxes? I didn't make it. Yeah. If I had drawn that x-axis at the front, or on the first one, we wouldn't have 3, we'd only have 1. The other thing, almost 4 zeros. Zeros are what? X-intercept. So if this is my x-axis, 1, 2, 3, 4 zeros, yes? And so again, I've just given you an example where you just saw the most. But what if that x-axis was drawn higher up? Would there still be 4 zeros? No, there would only be 2 zeros. Okay, so the idea is that's the most possible depending on how the graph is drawn and where the x-axis is. Okay? Now, that is a good stopping point. We will continue tomorrow. I think these notes are going to take longer than I want them to with everything going on. Those of you in class, you can see there's a Tuesday assignment and a Wednesday assignment. I've just given you the whole assignment for the whole thing. Those of you virtual, if you look in Skyward, there are 2 different page 193 assignments. And that's what, I'm just going to end up probably combining them with so many virtual. There's nothing due until we get done with the lesson. You can start looking at it, but we still have a lot of time to go. So it's the page 193, 2 through 8 evens, 9 through 12 all, 18 through 28 evens. I mentioned those yesterday. And then there's also 34 to 54 evens. And I forgot, I'd even written that down and I forgot to put it on here. Okay, so we will be getting more of that eventually. Have a good day, everybody.